Hello everyone and welcome to your 511-1 practice exam question. This video will cover the topics of kinetics with rate equations, nuclear decay, reaction coordinate diagrams, and rate laws. So let's first begin with a general review of the above. So we have rate laws, which are typically given as the change in a concentration per time is equal to something, either a rate constant or a rate constant times various concentrations to certain powers. The most common ones are zeroth order, where the rate is equal to a constant, first order, where the rate is equal to a constant times a concentration, and second order, where it's equal to a concentration squared times the rate constant. All of these can be integrated, as you can see, to give various equations, and all of them can compute a half-life, which is the amount of time it takes for half of the original reacting substance to remain. Now, the most interesting case for these equations is first order, because that's the one that corresponds to nuclear decay. And you'll notice the interesting thing about this is that the half-life doesn't depend on the initial concentration, so it's a value you could put in a table, for example. And that gives us the ability to do things like carbon dating. Another useful topic for us is the reaction coordinate energy diagram, which gives the energy of a reaction as it proceeds over time. And so you have the energy of the reagents farthest to the left, you have the products farthest to the right, and you typically also have some sort of hill or hump, which has a height equal to the activation energy in each direction. So the activation energy is the amount of energy you actually need to clear this hill from whichever ledge you started on. Delta E is the difference between the two ledges, which is related to thermodynamics, most specifically usually delta H, whether it's exo or endothermic, and you can use the temperature of the surroundings if you have enough energy to overcome the barrier and switch between the ledges. And this works in both directions, but obviously as the height of the barrier is different for the two directions, it doesn't work equally well. Now, another thing to notice is that catalysts have a very specific effect on the reaction coordinate diagram, which is that they lower the activation energy. They don't mess with any of the thermodynamics, they just make the hill smaller. And a final topic that we want to review today is the procedure for determining rate laws from a reaction mechanism. So we can never prove a mechanism, but we can decide whether a reaction mechanism has a rate law that's consistent with experiment. And to do that, the first thing we do is we know that the mechanism is a series of elementary steps. So we write rate laws using just whatever step is most relevant, and we let that include the reaction intermediates, which eventually we're going to have to get rid of. Then we make the steady state approximation, which is that the rate changes of the concentrations of the intermediates are zero. So at that point we have some equations that we can solve for our reaction intermediates. We can plug them into the rates that are interesting to us, and we can adjust for slow steps and make additional approximations at that point if we care to. So with those aspects of the review in mind, let's go to some questions that deal with this topic. So in question 7 of our practice exam, we're given a situation where we have a DNA double helix forming and a two-step reaction mechanism has been proposed. And we want to start out by just simply indicating the molecularity of each step. So the molecularity of the first step is going to be bimolecular because we have an elementary reaction. So in order for this to happen in one step, A and B must collide. By contrast, the molecularity of the second step is unimolecular because we have one thing that is changing into one other thing, so there doesn't need to be a collision, only one molecule needs to be involved. So it's at this point that we can consider what the rate law for the mechanism that's been proposed for this formation of the stable helix is. And it allows us to use the steady state approximation to eliminate intermediates, which is of course convenient because that's the way we know how to do that. So the first thing we do is we set up the rate that we're asked for, and the only place that SH is being made from is step 2, so we simply write the rate law for step 2. And then at that point we need to do the steady state approximation because the unstable helix is an intermediate and it's not something we can keep. So for the steady state approximation, 0, which is the rate of change of the unstable helix, is going to have 3 sources. So the rate of change of the unstable helix is increased by the first reaction running forward, decreased by the first reaction running backward, and decreased by the second reaction. So we have the rate law for each of those with the appropriate sign. And that's the setup of our steady state approximation. Now, at this point, what we can do is a series of algebraic things to solve for the intermediate, and we get a value that's in terms of things that aren't intermediate and in terms of the rate constants. We take that back to step 1 and plug it in for the value of the concentration of the unstable helix, and now we have our rate.